Welcome back. Today we're going to talk about graphing quadratic functions. Okay, so the first function we're going to talk about is f of x equals x squared, and this is what we're going to call a parent function. This is the simplest quadratic function that we can graph. All it does is it simply takes an x and it just squares it. So for instance, -3, remember that would be -3 quantity squared would be -3 times -3 would get you 9. -2 quantity squared would be 4, -1 quantity squared would be 1, 0 squared is 0. And then what you'll notice is that it's symmetric about this point 0. So it goes 9, 4, 1, 0, 1, 4, 9, and it continues on like that. So quadratic functions have this particular quality where they're symmetric about a certain point. And that's something we're going to talk about a little bit later in the chapter. So when I start to graph these, at -3 it is 9 right here. At -2 it's 4. At -1 it's 1, and at 0 it's 0. And what you'll notice is that at 1 it's 1 again. So you'll see that it's symmetric, and actually the parent function is symmetric about the origin, as it's actually symmetric about this line, this y-axis. So meaning that this one's 1 away, they're each 1 away from the y-axis, 1 on the left-hand side, 1 on the right-hand side. So when I graph 2, I get 4. So again, you see that each one has a distance of 2 away from the y-axis. And when I graph 3, I get 9. Now remember, I could have graphed 4 and -4. I could have graphed any number in between. I'm just using integers as a value that I'm graphing, right? I could have graphed, I could have checked 1.5 squared if I wanted to and graph that. I could have checked 1.6 squared and graph that. So there's an infinite amount of numbers between these integer values, but I'm just choosing these so that I can get a feel for how the parabola looks. So here's the graph of the simplest quadratic function. This is called the parent function. The U shape that it creates, that any quadratic function creates, is called a parabola. Okay. That's for any quadratic function. Remember, quadratic functions are those that have the highest exponent you see is a 2. So those are called quadratic functions. Now the bottom part of the quadratic function, this part right here, is called the vertex. All right. And if a vertical line is drawn through the vertex, it creates a line of symmetry, meaning I could fold the parabola about this line, and one side would match the other side. It would lay directly on top of it. So this branch here, this left branch, would lay directly on top of the right branch if I folded it along the y-axis. Okay, another way of describing that is it's called a line of symmetry. All right, there's a few things I want you to notice about this graph. It's going to make it easier for us later on. So for instance, you'll notice when you have at the vertex, the next point is 1 to the right and 1 up. So this is 1, 1. The next point is 1 to the right and 3 up. So I go from right 1 and up 3. And the next one is 1 to the right and 5 up. And you'll notice this 1, 3, 5 is going by odds. Same here. This is 1 to the left and 1 up, 1 to the left and 3 up, and 1 to the left and 5 up. And that's going to make it easier to graph some more functions later on. Okay. What we are going to talk about quickly is the domain and range of this quadratic function. Now remember, the domain is all the x values I'm allowed to put in. Now this is pretty simple. Remember, most functions have a domain of all real numbers, except those that create zeros in the denominator. And there's no denominator here, so I'm allowed to put any real number in here. Remember, real numbers are rational numbers and irrational numbers. So I could actually take an irrational number like pi and square it. I could take an irrational number like square root of 2 and square it, and actually just get an integer back, which is 2. So the domain here is all real numbers. Remember, that's like a bolded R with a second line there to indicate bold. What is the range of x squared? Now, the range is all the y values that come out of the graph, all the output values, right? So if you'll notice, this is special because it doesn't get there's no number that I can square to get a negative y value. So here, all the values that output from this function are just the positive real numbers. So all positive real numbers. All positive real numbers, and also 0. Another way of saying this is all non-negative real numbers, because that would include 0. So that's another way of saying the same thing. Okay, so that's the domain and range of the parent function. Now the vertical shifts, we're going to talk about vertical and horizontal shifts today. And a vertical shifts happens when you have the parent function. Remember, the parent function is just this function right here. F of x is equal to x squared. A vertical shift happens, so this whole parabola shifts up and down if you add or subtract a number outside of the parent function. So here you have the parent function. If you have the parent function and then you just add or subtract a number outside this x squared, then it shifts up or down. So you'll see here, what I've done is I've graphed this g of x, which is x squared plus 2. And what you'll notice, this is the original function here, right? We went from 0, 1, 4, 9, 16, 25, 36. And what I've done is I've just taken all the original outputs, which is here in this column, and I've just added 2 to them. So instead of 0, we get 2. Instead of 1, we get 3. So I've just added 2 to both all of these outputs, because that's what this says right here. After you square the x, then you add 2 to it. Well, what ends up happening is, just imagine, you're not changing any of the x values, right? You're not changing any of the values that go into the squaring function. What you're doing is you're changing all the output values. Now, this makes sense that it's a vertical shift because the output values are your y values. So literally, you're just taking your old y values and you're adding 2 to it. What happens when you do that? It shifts it up, right? So your old parent function, this right here is f of x is equal to x squared. And this one that's inside here, it's the identical shape. So it's identical shape, but it is just translated upward. And translation is just a slide. So this is your g of x right here. Okay. Now you'll notice this happens when k is greater than 0. It shifts upward. But if k is less than 0, meaning it's negative, then it will shift downward. So if it's x squared minus something, it will shift downward. If k is equal to 0, well, then you have the parent function. So here is an indication, this is x squared minus 2. Now again, what you've done was you've taken the original parent function right here and you've just subtracted, like 9 minus 2 is 7, 4 minus 2 is 2, 1 minus 2 is negative 1. So you've just subtracted off 2 from all of the output values to get your new function h of x. And you'll notice this is h of x, it's just shifted downward. And again, you have the same shape, it's just shifted downward. It has the illusion of being opening more, but that's just because we're seeing more of the parabola because it's been shifted downward. So the window is showing more of the parabola. But if you were to take this whole thing and let's see, grab it and push it upward, you would get the same shape up here, right? That would be the same right here, okay? Okay, now horizontal shifts work in a different way. Horizontal shifts are taking something and attaching it to the x before you square it, right? The parent function is just taking the input and squaring it. So if you take the input and you sort of mess with the input before you square it, it will make a horizontal change. So here you have x plus k, and that quantity is being squared. So for instance, we have x plus 3 squared, and it works in the opposite way than we would intuit, or we would that we would think that it would work, right? So here's your old parent function. This is f of x, right? It's negative 3 quantity squared is 9, so we have that 9, 4, 1, 0, 1, 4, 9 integer values here. But what it's doing is it's taking, it's adding 3 to the x value and then squaring it. So it takes negative 3, adds 3 to it to get 0, and then it squares 0 to get 0 back, right? Negative 2 plus 3 gets you 1, and 1 squared gets you 1. So here it's taking, it's adding 3 to the input, not the output. That's why it shifts along the x-axis, because that's the input value. But notice that it shifts in the opposite way. So for instance, what used to be the vertex, which was 0, 0, now becomes the vertex of 3, 0, right? So here it shifts to the left by 3, not to the right. So again, horizontal shifts work in the opposite way than we think there is. When k is greater than 0, it shifts to the left. When k is less than 0, it shifts to the right. When k is equal to 0, it's the parent function. Okay, that's because the thing that you're squaring ends up being, in this case, it changes the way the input value works, so it's squaring a different number than it used to. So here, Here we have the function where the number that we're using right here is less than 0. It's going to shift to the right. So here we're taking 5 away from every input value and then squaring it. So what you'll notice is we actually have, for the negative numbers, it actually makes them more negative. So negative 3 minus 5 is negative 8, but negative 8 quantity squared gets you a large number, 64. Whereas if you have 0 here, 0 minus 5 is negative 5, but when that's squared, it gets you a positive 25. So the numbers actually end up being, the output values, look, where it used to be 9, now it's 64. Where it used to be 4, now it's 49, and so on. Right? So it takes all the output values and it makes them very, well, it takes the input values and it takes away 5 from them, but it doesn't matter if it becomes more negative, because then when you square it, it becomes larger. So what ends up happening is it shifts it to the right by 5, okay? And again, it's that opposite direction that we're seeing here. Okay, so if we're talking about these shifts in terms of, in general, our parent function is f of x equals x squared. So there's two sorts of shifts. We can have x minus h, and the h is a horizontal shift. That can happen before it gets squared here. And then we can add a k on the outside, which is adding it to the output values. Here, the parent function has a vertex of the origin, right? 0, 0. And the vertex of these shifts becomes h comma k. So h meaning it shifted along the x-axis by a positive h amount. Remember, if it's minus h, it actually shifts in a positive direction. And the k, if it's plus k, then it shifts up. So now your vertex is, it shifts positive and up in this case right here. So let's say you had f of x is equal to x minus 3 squared plus 8, your vertex would be 3, 8. Whereas if you had f of x is equal to x plus 5 squared minus 10, your vertex would be negative 5 comma negative 10. So you always do what's the opposite of the inside here, and you take the face value of the outside k value. Okay? Okay, so let's just try our hand at writing the equation for the parabola below. All you have to really do is make sure, first of all, that the opening is as wide as the original parent function. And here, remember, if we start at the vertex, we go up 1, 1, 1 is our first change, and then we go up 1 and up 3, right 1 and up 3, 1, 2, 3. Whoops, 1, 2, 3 right here. Another 1 and 3, and then we go right 1 and up 1, 2, 3, 4, and we can't really see it. It should be 5. Okay, so the opening is as narrow, or it's as open as wide. The u is open as wide as the parent function. Now all I have to do is look at the vertex. So here, this is 3, 2. Okay, now let's think about it. This would be f of x is equal to. Now we would have to do x minus 3 because it's always the opposite of what's inside. So this is a positive 3. We're going to make this minus. And we put this one, the y shift at face value, which is plus 2. Okay, so here, let's see, our vertex here, so again, we'll make sure that it's opening, that's 1, 1. The next one will be up 1, 2, 3. Okay, so it's, and the next one will be right 1 and up 1, 2, 3, 4, 5. So these, and we don't have to check the other side because remember, it's symmetric about the line going, a vertical line going through the vertex. So as long as it has that pattern, up, right 1, up 1, right 1, up 3, right 1, up 5, then we know the opening is as wide as the parent function. So all we have to do is do the shifts h and k. So here the vertex is at negative 4, negative 5. So we would have, let's call it g of x. G of x is equal to, now it would be x plus 4, because it's the opposite of this one, squared, and minus 5. We take the face value of the vertical shift. Okay. Finally, if we're asked to graph, okay, first we'd have to indicate whether or not it's a vertical shift, a horizontal shift, or both. Here, this is a vertical shift that's on the outside. So here my vertex is going to be 0, 4 because it's just being shifted upward from the original vertex of the origin. It's just being shifted upward 4. So there's that. And then remember, we just go right 1, up 1, right 1, up 1, 2, 3, and right 1, up 1, 2, 3. We can't do it that far. And remember, The line through the vertex is the line of symmetry. So here, I can cross this line of symmetry and make the points on their side. This one's 2 away from that line, so it's going to be 2 to the left, and so on. So here is my parabola like this. Okay, let's try our hand at one more. This is x squared minus 5. So here again, this is a vertical shift. My vertex would be at 0, -5. So you would have 0, -5 here. And we'll do that up 1, right 1, up 1, right 1, up 1, 2, 3, and right 1, up 1, 2, 3, 4, 5. So it would be about here. And again, the vertical line through the vertex is the line of symmetry. So here I can use this to find other points here. So this would be about, remember, all I'm doing is like sort of mimicking this distance, but on the other side of the line of symmetry. So here we go. Okay, so there is how you graph it. I just used the characteristic of the parent function, and I just changed the vertex a little bit. All right, and that's the end of the lesson for today.